5.1b. We're working on inverse functions some more, and so we're going to look and see what some applications of the inverse functions, but also just doing some different calculations with them. A little bit of review first. The graphical relationship between inverse functions. So if you plot your function and what you believe to be its inverse, they should be reflected across the line y equals x. If you're looking at the xy tables, the x and the y coordinates are swapped. So you take all the x coordinates and put them in for the y's on the inverse function. So if you have, here's an example, if we have x cubed as a function, we'll call it f of x, and we write a couple ordered pairs for it, then you can see on its inverse, which happens to be the cube root of x, that you have the same y value as what was the x value. And then similarly, the y value for the function is swapped into the x value position. And the same deal for the any other ordered pair that you have for that function and the inverse. If you're looking with algebra, here's a little example of how it all works. The cube root of x undoes what's being done by x cubed. So what we expect to see with inverses is that if you plug in, say, a 2 for the function, so you're plugging it in and you're cubing it, and then you get 8. Then we plug in the 8 into the inverse, or what we suspect is the inverse function, and it's the cube root of x, so it's the cube root of 8, and we end up with 2. So the point here is that what you did is undone. So whatever you started with, you end with, and the two functions act inside, but one undoes the actions of the other function. So if we look at it in the order starting with the function f, for an inverse we also want to have it work in the opposite direction. So up here, this one is f of g of x that we're showing there. And down here, this one you can see we're handling the g function first, so this one is g of f of x. So we're taking the 8 and feeding it into the function, so the cube root of 8 is 2, and then feed that into the next function, the f function. So we feed in the 2 and cube it, and we end up with 8. So our initial input is the same thing as our output from the string of the two functions. So when we put them in composition with one another, we end up with what we started with. And here that is formally the composition of functions is applying the two functions in succession. In math, if we have f and g of x and we say they're inverses, then two things have to be true. If they are inverses truly, then if we do f of g of x, we should end up with x. So whatever we put in, we come out with that same number. And the same thing in the other order. So if we do g of f of x, we expect whatever we stuck in initially to be what our output is as well. So that's the formal way to write that. Then in terms of notation, if g of x is the inverse of f of x, and we talked about this last time, we could also call g of x f inverse of x. And remember the horizontal line test. So if we have a graph, like that for example, if a horizontal line crosses the graph in more than one place, then this function does not have an inverse function. And remember, it does have an inverse, but the inverse is not a function. And remember also, in the last assignment, you were able to specify part of the domain so that you could make the resulting function an inverse, the resulting inverse a function. Say that again. So let's look at some examples. And this is, say I give you two functions and I tell you, hey, these two are inverses. And like usual, you shouldn't believe me. So you're going to try it out and see if I'm right. We're going to look at it two different ways. One by graphing to see if they look like inverses or not. And second, algebraically to prove whether they're really inverses or not. Okay, the first thing I want to do is graph this. f of x, and then I also want to graph g of x. So go ahead and pause the video and then do that yourself and then compare to what I'm coming up with. So to graph f of x, I want to look at x cubed because that's my parent. And so I'll look at x and y for x cubed. So I'll probably want a 2, -2, -1, 0, 1, and 2 because I'm thinking about the shape of that. I know it's pretty much centered at 0 for the parent. I want 2 points on either side. I don't want to go further because the numbers get giant really fast. So -2 quantity cubed will give me a -8. -1 quantity cubed, -1, 0, 1, and 8. So that's my parent function. I don't really want to graph that, but I want to use it to make the transformations because I want to do here this +2, and it's inside the parentheses of what's being cubed with the x. So it's acting on the x. So since it's +2, we have to do the opposite, remember. So we're going to move to the left 2, and that means we're going to subtract 2 from our x's. So for the x +2 quantity cubed, I have one transformation, and it's going to be subtract 2 from my x's. My y's are going to stay unchanged. So I can just go ahead and write out the y's like that, and then subtract 2 from my x's. So -2 - 2, -4, -1 - 2, -3, 0 - 2, -2, 1 - 2, -1, and 2 - 2, 0. Now that is the f of x function, so I can go ahead and plot it. So it's -4, -8, it's right there. I have -3, -1, -2, 0, -1, +1, and 0 all the way up at 8. 1, 2, 3, 4, 5, 6, 7, 8. Right about there. Remember, this is a cubic, so we expect it to have this snaky look. And then I want to graph the g of x. Oh, first, before I go on, make sure we mark that. That one is f of x. And I've noticed on your paper it's really hard to see your graphs if you're using plain pencil, so you might want to try some colored pencils or draw them in pencil, and then when you're sure that you've got it right, copy over it with a colored marker. Okay, so next we should do g of x, and it is the cube root of x minus 2. The parent on that is the cube root of x, so I'm going to do a few points here. I'm looking for perfect cubes, so I know -8, -1, 0, 1, and 8 are all perfect cubes. Plug them each in the cube root of -8. That'll be -2, -1, 0, 1, and 2. And then I have to do this transformation on it, and that means I'm going down 2, so that's happening to the y's. So I'm subtracting 2 from the y's. So if I do my xy table, this I'm going to subtract 2 from it. And that will give me the cube root of x minus 2. So same x's, not changing them, -8, -1, 0, 1, and 8. And I'm subtracting 2 from each of my y's. So -2 minus 2, -4, -1 minus 2, -3, 0 minus 2, -2, 1 minus 2, -1, and 2 minus 2, 0. Okay, go ahead and plot those. So I have -8, -4, 1, 2, 3, 4, not really there at 0, and then -1, -3, 0, -2, 1, -1, and then 2, 3, 4, 5, 6, 7, 8, 0. There's my 0. All right. It's going just like we had for the f of x, except that it's turned on its side. So this one is my g of x. Make sure I label it. so that when I'm grading anything you've done, I can tell which one you meant to be your f of x and which one was your g of x. Now, from the graphs, the next part, from the graphs, do you believe these two functions are inverses? And to answer that, I really want to draw in that line y equals x, and then consider, does it look like this point is the opposite of that one, and so on? Do they all look like they've been reflected over that line y equals x? And they really kind of do, right? It kind of looks like they're the same distance on the opposite side. So it looks like they are inverses. Now I can do one other check on this one, and it's easy to tell because I happen to use the same points. But from my translated graphs, so I'm talking about this one and I'm talking about that one, the two that I actually made my graphs on the chart from, are they opposites? So like what I have in my y column for my f of x, is it my x column for my g of x? And for what I have in the x column for my f of x, is it my g column or my y column for the g of x? And it looks like they are, because here I have 0, 8, 8, 0. Here I have negative 1, 1, 1, negative 1. So they are exactly opposites. 0, negative 2, 0, 0, negative 2. So I really expect that these two are inverses. And then it says if you believe that they are inverse functions, verify by using the definition of inverse functions. And I'm going to tell you, I want you to go ahead and verify whether you believe they're inverses or not, because that will be your final proof of if you're right, if they really are inverses. First thing I'm going to do is rewrite my two functions so they're right here where I'm looking. And this one was, it's the quantity cubed x plus 2, quantity cubed, and my g of x, that was the cube root of x minus 2. Okay, so first thing I have to do is f of g of x, and I'm thinking it should be x. If they're really inverses, I should end up with x. And then another check I need to do is g of f of x, and that one should come to x as well. If they both come out to x, the two functions are inverses. So let's try it out. So first, f of g of x, and that means I'm doing f of g of x, which really looks like I'm plugging in the g of x into the f, right? That's what it's supposed to look like anyway. So f of, and then I have, here's my g of x, cube root of x minus 2. And my function f is some quantity, which is my x, plus 2 cubed. And what I'm going to do for that is take what I'm supposed to plug in and stick it in there where that x is. And I'm showing it kind of graphically because I know this gets confusing for some people. So hopefully this will help a little bit. So then what I have, what I'm looking at is this quantity, cube root of x minus 2 plus 2. And then that whole thing is being cubed. Now inside those square brackets, I want to simplify. And the first thing I'm wondering is, do I have to keep those parentheses? And I don't. There's nothing outside of them. There's no negatives that I'm trying to distribute or anything else. So I can just drop the parentheses. And then the next thing I'm looking at is, can I combine any like terms? And I see I have a negative 2 and a positive 2, and they not only combine, but they cancel. So I'm left with cube root of x, and I can change to regular parentheses now because I don't have a couple layers of them. Cube root of x cubed. And the cubed and the cube root are the opposite operations, so they undo one another. The cubed and the cube root undo, and I'm left with x. Well, that's what I expected, isn't it? Up here where I said if I end up with x, that means I'm partway there figuring out if they're inverses or not. So let's look at the second one then, the second step. So now I need to do g of f of x. And that means I'm doing g of little bitty f of x, g of, and f of x is x plus 2 quantity cubed. And I'm sticking that in for g. I need to move down just a tad, it looks like. Yep, that'll work. Okay, so then when I'm sticking that into g, g is the cube root of whatever your x is minus 2. So get my purple pen again, and I'm taking that thing I want to stick in for x and sticking it in where there was an x in the original. So rewrite one more time here. So I have the cube root, really big, x plus 2 quantity cubed minus 2. Now, since I only have one quantity being cubed under the cube root, this whole thing is being cubed, so it'll undo with this cube root. It has to be just the one term. If I had a sum under there that was two pieces, one of them was cubed, I can't get rid of the cube root. I would have to have just one term cubed under the cube root. And I have that in this case. So I end up, my next step is to write out, I have x plus 2, and then from the other part, a minus 2. My 2 and my negative 2 like terms, and they actually cancel. And I'm left again with x. Now that's what I expect if these two functions are actually inverses. So I know now that f of x and g of x are inverses of one another. So that's the specific way to state your answer there. Okay, so looking at another one here. This should be a little bit of review from 5.1a. We want to graph this f of x, and we want to graph this g of x. So let's start with the f of x. And if you know how to do this, or you think you remember, go ahead and pause the video and try it by yourself. You learn way more than just watching. So f of x equals x plus 3 over x minus 2. First thing I want to find is vertical asymptotes. And I know my vertical asymptote is going to come from that denominator set to 0, which gives me x equals 2. So that is my vertical asymptote. I guess I'll leave it as black. And I can mark that in. And I'll write above it x equals 2, just so I have it marked. Then I want to know if I have a horizontal asymptote. And remember, for the horizontal asymptote, it's going to be the ratio of the lead coefficients. And the reason it's that is because my two lead terms have the same degree. Now remember, it's a little bit different if the degrees aren't the same, but on this one it's a degree 1 and a degree 1. So I take the ratio of the two coefficients, which are implied ones, so 1 over 1 or 1. So y equals 1 is my horizontal asymptote, so I will mark it in. And then I'm ready to do an XY table. Now remember that I know x equals 2 is where my function's undefined, because that'll give me a divide by 0. So that's also kind of the middle point of my XY table. So I'll put that's undefined right there. And then I'm going to do like 3 points to the left of 2 if you're thinking on the number line, and 3 points to the right of 2. So 3 points smaller, 3 points greater. So 2, 1, 0, negative 1. And then 2, I'm going to go 3, 4, 5. All right, so if I have negative 1, I'm just plugging it in to this function here that I kind of made look really ugly. So let's see if I can clean it up. There, so I'm plugging it into this function f of x. So negative 1 on the numerator, negative 1 plus 3 is going to give me 2. Negative 1 minus 2 is going to give me a negative 3. So it's going to be negative 2/3. Plug in 0 and I end up with negative 1.5. Plug in 1, end up with negative 4. Plug in 3, end up with 6. Plug in 4, end up with 3.5. And I really encourage you to make sure that you can calculate these as well on your own. And plug in 5 and I end up with 2 2/3. So I'm ready to graph. Remember, I have two pieces. I have two pieces, one on either side of my asymptote, one piece on either side. So on the left-hand piece, I have negative 1, negative 2/3. So negative 1, negative 2/3. And then I have 0, negative 1.5, and 1, negative 4. Okay, now remember the shape. I've got the part right there, but I know it's approaching my asymptotes as it gets further and further out, further and closer in towards my vertical asymptote. So it should look something like that. I should probably label that f of x, and I might need to move it. Let's check the right hand side. So it's 3, 1, 2, 3, and up 6. 1, 2, 3, 4, 5, 6. So right there. 4, 1, 2, 3.5, and 5, 2 2/3. There. And then we're going close to our asymptotes in both directions, and that's not perfectly smooth. Let me give it one more shot. That looks much better. Okay, so there's my graph of f of x. I wrote it all in black, so I can mark it one time f of x in black, but if not, then you definitely, if you have only one color for both of your graphs, then you would want to mark both pieces with your f of x. And now I would like to graph g of x. 2x plus 3 and x minus 1. First thing, again, I want to know the vertical. You guys go ahead and pause and try this one out because you saw me do one of them, so you got all the bugs worked out. Now you try one and make sure you can do it on your own as well. Please. So I'm looking at the denominator, x minus 1 equals 0. And that gives me x equals 0. I mean 1. And then for the horizontal, I'm looking at the lead terms. They're both to the first power, so they have an equal degree. So I'm going to take the ratio. So y equals the ratio, which is 2 over 1. Remember, it's just the lead coefficients there, and it comes to 2. So there's my two asymptotes. I can draw them in. I have y equals 2, that's up here. And then I have x equals 1, so that's going to be in here. And this one's kind of tight. All right, and then an xy table. Same thing, I'm looking at this one. I know it's undefined at x equals 1 because that's where I end up with a 0 for my denominator. So I'm going to put 1 in, that's the center basically, because it's not defined at 1. And then I'll give like 3 points that are to the left or smaller than 1, and then 3 points to the right or larger than 1. So I have 1 and 0, negative 1, negative 2, and then I have 1 and then 2, 3, 4. Okay, I'm plugging them into the g of x function here. So I have negative 2 times 2, that'll give me negative 4 plus 3, so a negative 1 over negative 1 over negative 2 minus 1, so negative 3. So that gives me It was a negative 1, yeah, so positive 1/3. And then negative 1 times 2, negative 2 plus 3, that'll give me a 1. And then negative 1 minus 1, negative 2, so negative 0.5. And then I'll give you some other points here. 0 gives you a negative 3, 2 gives you a 7, 3 gives you a 4.5, and 4 gives you 2 2/3. Okay, so I'll go ahead and graph those in chunks again. The left-hand side is going to be negative 2, positive 1/3. So negative 2, positive 1/3. And then negative 1, negative 0.5. Looks like it's right on that same point. And then 0, negative 3. 1, 2, 3. Right there. So now I know I'm going to the red asymptotes. You can probably see why it would be a good thing to get colored pencils or pens now. And then my second set, on that one I can label g of x, and on my right hand side I have 2, 7, so 1, 2, 2, 7, 3, 1, 2, 3, 4.5, and 5, no, sorry, 4, 2, and 2/3. 1, 2, 3, 4, 1, 2, 2/3. Okay, there we are. And again, going to the red asymptotes. And that one is my g of x. Okay, so there's my two graphs. Then the big question, do they look like they are reflected over that line y equals x? Do they look like they're inverses? And most of the students today said no, they don't. So no, maybe not. Because we're really not very good at judging yet on these inverses. So I'm going to tell you, whether you believe they're inverses or not, verify it using algebra. So if you think they're not, that's fine. You write down, no, I don't think so. And if you think they are, write that down. But either way, I want you to do the check algebraically. So let's see what that involves. First thing, remember, we need to do f of g of x, and we're expecting that to come out to x. And so to do that, I need to do f of g of x, and I think before I even write that, I want to write what my f of x is, because it's a fraction. X plus 3 over x minus 2, and my g of x
schedule kind of messed up. I don't know.
Okay, we want to find f of g of x, so that'll be f of g of x, and that'll be f of my g of x is big, 2x plus 3 over x minus 1. And when I plug that into my f, I have x plus 3 over x minus 2. So remember that whole thing that was my g of x is what I'm sticking in to both spots. So it's going to look like 2x plus 3 over x minus 1 plus 3 all over 2x plus 3 over x minus 1 minus 2. Now that's a complex fraction. So the way we handle complex fractions is we make sure every term is represented as a fraction just because it looks better to our eyes that way. So I'm going to put those over 1. And then I want to look at all 4 of my denominators now and find the common denominator. Remember this denominator here, the x minus 1, and then I have 2 1s, so it's x minus 1 is it. That's my common denominator. Remember we multiply by this, our own complex fraction, x minus 1 over itself, and I put it over 1 so it's in fraction form, and remember I'm distributing. So this will multiply by that term and by the first term. Same thing on the denominator. Each term is going to multiply by the x minus 1. And I left a little space because it's really handy if I go ahead and just write it x minus 1 over 1 here, and then the x minus 1 over 1 here. So every fraction, every term has its own x minus 1 over 1. Now I can reduce things. So these x minus 1s go, and those go. This 3, I'm going to erase these distributes because we already did that. The 3 is going to have to distribute there, and this negative 2 is going to have to distribute here. All right, let's take a look at what happens with that. Good thing we have a lot of space there. So then on the numerator, I now have this 2x plus 3 here. So 2x plus 3. And then I have plus 3 times the quantity x minus 1. So I want to distribute, so it'll be plus 3x minus 3. Denominator, I have a 2x plus 3 again. And then I have negative 2 times the quantity x minus 1. So go ahead and distribute negative 2x and then a plus 2. Okay, I want to simplify more, so that means combine like terms. You can't cancel anything because we have several terms, top and bottom, so we have to simplify. So but you can cancel if it's all on the top. So I have a plus 3 here, a minus 3 here, they do cancel. In the denominator I have a plus 2x and a minus 2x, they cancel as well. I want to write what I have left, 2x plus 3x, that gives me 5x. And the denominator 3 plus 2, so I have 5, and that simplifies to x. So starting to look like they might be inverses. Let's take a look. This is half of what I have to do. So I also need to look at g of f of x, and just think you're getting a lot of practice on complex fractions again. So I have g of f of x, which means I want to do g, the function g, but I want to stick in f of x, and f of x is x plus 3 over x minus 2. Okay, so I'm going to look at g. How about if I move that down just a tad so it's not in the way? Okay, make sure I have enough room. Move it up just a hair. Okay, that should work right there. Write my functions, and then I can scroll down. So I know this should be g. I'm looking at g, so I have 2 times whatever x is plus 3 over whatever x is minus 1. Remember, I'm plugging in. And if you have trouble on these, just show it like I'm showing it so that you can figure out what's happening in each step. So what I have now is 2 times the quantity, x plus 3 over x minus 2 plus 3, denominator, x plus 3 over x minus 2, and I have nothing out front, no negatives to distribute or any numbers or anything, so I don't need the parentheses on the denominator, and then it's just a minus 1. Now I'm looking across this problem. I've got several parts that are not fractions. So I'm going to turn them into fractions, and this is being multiplied, so the 2 times the quantity, that's all one term. So when I'm looking at denominators, you can see that it's x minus 2 over 1, x minus 2 over 1 that I need to be multiplying by. And remember, I have to distribute. Every term in the numerator needs to get an x minus 2 multiplied by it. So this term here on the left, x minus 2 over 1 times there, and this one here as well. And then I can start looking at reducing. So here, my x minus 2's go, and here my x minus 2's go, and everything else I'm just going to have to multiply out. So this 2 is going to be distributed here, and this 3 likewise distributed here. A negative 1 will be distributed here, and I don't have anything that's happening to that x plus 3, so I'll just be writing it down. I think we'll be able to fit it. Let's check. So I have 2x plus 6, and then distribute that positive 3. So plus 3x minus 6. That's my numerator. My denominator, I have that x plus 3, and then minus 1 times the quantity x minus 2. So minus x plus 2. Okay. I keep thinking I've done something wrong, but it looks okay. We're doing fine. So plus 6 minus 6, they cancel. The plus x minus x cancel as well. Now I'm just writing out combined like terms and write out what you have left. 2x plus 3x, 5x, 3 plus 2, 5. That comes to x. And so I know g of x and f of x are inverses of one another. Let's look at one more type of problem, and this one's a word problem. So we're looking at, for those of you who are wondering, when do we ever use these? Here's an example of what we would want to use these for, and you'll have another example on your homework. Okay, so we have this equation, y equals 0.432x minus 10.44. First, I need to sketch the function, and I also need to sketch the inverse. So for the function, I want to pick out, I want to make an XY table and pick out a few points that I think are important for this. When I look at this, the X is the height of a female and Y is the length of the female's femur. So imagine that you're out doing a dig for archaeology and you find a bunch of leg bones and you're trying to figure out, you figured out that they were from females, and you're trying to figure out. So if you go on a dig and you find a bunch of thigh bones from that you determined are from women, you could plug them into this formula and find out how tall the woman was. Or the other way around, for different women you can estimate how long their femurs were, or are if they're still alive. So I thought about some values. I wanted to know what would happen when y was equal to 0, because that would be the point where it's going to be touching my x-axis. So I just set it equal. 0 equals 0.432 x minus 10.44. And to find x, I just add 10.44 to both sides. And I have 10.44 equals 0.432x. Divide both sides by 0.432. And I get x equals 24.16. And I had to round, it doesn't come out exact. Okay, so in addition to that point, so that's telling me that's the smallest point that's going to give me a positive value, and everything to the right of it will be positive. But I thought 50 inches was a good length or height of a person, 60, 70, and I did 80 as well. So I'm going to plug each of those into the formula, and I'll have it as y equals 0.432, plug in whatever your x is, minus 10.44. So I was using it in this form because remember I'm supplying the x's, I want to find the y's, so it'll be in that form. What I came up with for 50 was 11.16. You can double check these. 15.48, 19.8 and 24.12. Okay, so when I go to graph, oh, excuse me, when I go to graph, I'm looking for some kind of scale that I can use that's going to be the same for my x's and for my y's. And I can see that my x's, I'm going up to 80, so I need to go at least to 80 on my graph. And the y's aren't going that high, but whatever scale I find up to 80 will seem to work. And then when I do the inverse, remember I'll need the up to 80 for the y part. So I'm going to use the same scale. I'm going to jump up by 5, so this will be 10 and 20, 30, 40, 50, 60, and 80. Same thing along the y-axis. I'm not numbering them all, but it's kind of obvious what I've got there. Then I can see at 24.16, and you're going to have to estimate where that is. It's real close to 25, right? So put a dot there. And then 50, 11.16, so go over to 50, there's 10, so it's just above 10. And I'm going to also plot 80, because that's up 24. So 5, 10, 15, 20, 24, right before 25. And now that gives me enough that I can make a pretty good graph, and I'll call that one f of x, even though it's listed as y equals. Okay, the next thing I need to do is graph the inverse. So I'm looking at f inverse of x, and remember when you're graphing and you already have one xy table and I know that they're inverses because I'm told to graph the inverse, then I can just swap the values for the x's and the y's, which makes it pretty quick. So 0, 24.16, and I think I graphed at 50, so we'll write that one down. Sorry, wrong side. That would be 50 on the right, and then 11.16 because I'm swapping them. And then I also did 80, so put down the 80 and 24.12. So there I have 0, go up 24.16, there's my point. 11.16, real close to 10, and all the way up to 50, right about there, and 24, almost 25, all the way up to 80, so about right there. So pretty steep going in that direction. And this is my f inverse of x. And do those look like inverses? Remember, we've been checking that. If I reflected them across this line, would it look like they were reflected? And it really does, so we're good. Now, determine the domain and the range for the function. So we're talking about the function here, and then we'll talk about the inverse function. So starting with the function, the domain is your x's, and in words, the domain is the height of the female. And so what heights are valid for this function? And you have to look where we hit 0 because we didn't want to have the negative values because those don't make sense for the length of a femur. So our function starts out defined at 24.16, but if you have that, then you have a length of 0 for your femur. So we're going to have to say it's not any good unless it's greater than 24.16. And then the highest height that you could have for a woman, you could calculate some number that you believe to be the highest and put it on there. But you can also say, well, this function is going to define it to infinity, so we could put it as going to infinity. The next thing we need is the range, and that is the y's for this function. The y's are the femur length, so femur. And when I look at, again, we're still on the f of x, so when I look at how high I'm going, we are starting at 0. We have a 0, and then we're going up higher and higher and higher. So this one we're going to say, yeah, 0 to infinity as for that, for the length of the femur. And parentheses at 0 because there's no femur if it's a 0. Okay, now thinking about the inverse. So now we're looking at this graph, and if we're doing the domain, remember going left to right, and we have a value here at 0, and then all the way it looks like we can go to infinity. So for this one, the domain, that's in the x's direction, and for the inverse function, remember we swapped our y's with our x's, so now our x's are the femur length, and that means that our domain is the lengths that we can have for a femur, so it's 0 to infinity. The range for the inverse is the y's still, but since we swapped our x values and our y values, our inverse function has whatever the original function had for the x's. So that would be the height. So we just swapped them. Femur went here, height went there. Okay, so we swapped those just like we swapped the two columns, just like we swapped the two elements in an ordered pair. So when we're finding the inverse, we're swapping. And then we look at the height. It's going to be the exact same height that we already figured out, so 24.16 to infinity. Things haven't changed, but look at the function. Now we're talking range, so we're going from that 24, from this point here on up for the range, and that is about that 24.16 to infinity. So that does make sense from our graph as well. Okay, nearly there, hang in there. Solve for the inverse algebraically. So remember we had our function started as y equals 0.432x minus 10.44. Remember, the first thing that you do is change it from f of x notation to y equals. It's already in that notation. So then we're just going to jump to the second step, which is to swap the variables. 0.432x minus, now that one's y, minus 10.44. And then the third step, we want to solve for the y. So I'm going to do the first thing, add the 10.44 to both sides. And I get x plus 10.44 equals 0.432y. Divide both sides by that 0.432, so I'm going to divide each one. This is a 1 in front, remember, 0.432 divided by 0.432. And these cancel as I expect, and I have y equals, putting it in the other order. And I have this term right here, 1 in the numerator divided by 0.432. So I'm going to just calculate that. 1 divided by 0.432, and I get 2.31. And the next digit's a 4, so I'm going to leave it as 2.31. So 2.31x. And then I have plus, but I know it's going to be another decimal. So I have 10.44 divided by 0.432. And I get 21.6666, so I'll change it to 24.17. So 24.17. And that's my function. The last step, remember, is to put it in inverse form. F inverse of x equals 2.31x plus 24.17. And And that one's pretty easy to do because it doesn't have any cubes or squares or anything like that. It's just linear. Remember, if you don't have cubes or squared or any higher degree, it's just a degree 1, it should be a perfectly straight line when you graph it. You can use your ruler or an ID card or the edge of your calculator, something like that, to make a nice straight line. It shouldn't be all curvy like any of the other graphs we've been doing. Okay, so now we're asking, and we kind of already figured it out, so it'll be pretty quick. What does each variable represent in the inverse function? Remember, we know what they are in the function, and then in the inverse, we actually wrote it down here. So the x represents the femur length, and the y, and this is in the inverse, remember, the y represents the height of the female. And it's exactly backwards. You can look right here in the initial part. We said that x was the height of the female and y was the femur length. X was the height of the female, y was the femur length. Exactly opposite of what we've got for what we defined for the inverse, and that makes sense. It should be exactly opposite. Okay, 2 more and then we're done. Determine the length of the femur of a woman who's 5.5 feet tall. So 5.5 feet equals how many inches? And to find how many inches, we can just multiply by 12, and so we get 66 inches. So a 66-inch woman, and since we have the height of the woman, we really want to use the function that you can plug in the height. And this function, I have it written right here. This function where we plug in x, it's the femur length, and that's not what we want to plug in. We want to plug in height. So we're going to use the regular function f of 66, which means it'll be 0.432, and this is from up above, times 66 minus 10.44. That's our original function, remember. Calculate that out, and I get f of 66 equals 18.07. And so I can say a woman who is 5 foot 6 inches, that's 5.5 feet, should have a femur that's 18.07 inches long. Okay, and that was pretty straightforward, right? Just plug it in, but you had to pick which function. That was the only thing you have to really think about there. Okay, so now I have a femur length of 20.66. I want to know how tall the woman is. So I want to plug in femur length, so I'm looking for the function that has femur length as the x. And that is my inverse function. It has x is the femur length, so I want to plug that in. So I'm going to do f inverse of 20.66 because that's where I can plug in the femur length. And using that function from part D, I'll sub it in, and so I have 2.31 times 20.66 plus 24.17. Okay, if I use the original formula, I have to do a lot more solving. So the inverse is a lot handier this way. And imagine if you're out in the field doing an archaeology dig and you have all these bones that everybody's found when they were digging, and you're the one who calculates how tall the women were. And so you're looking at, you've got say 100 femurs, and you've got to measure them all, plug them into a calculation. You want the quick one. You don't want to take a lot of time doing that. You want it to be quick. So the inverse function would be the function that you would be using over and over and over. So when I calculate all this out, I end up with 71.89, and that's about 72 if I round it, which is a 6-foot female Amazon, has a femur that's 20.66 inches. And I could put the word a at the front and that would make it just a perfect sentence. A 6-foot female has a femur that's 20.66 inches. Okay, that's it for this lesson.